Hello. So today we're going to talk more about ordinary differential equations, and we'll be doing the example that you see in front of you here. And let's just jump right in. So we go through our questions, right, as always. The first question is, what is the order of this differential equation? Well, I only see one derivative inside, and that's the dy dx, and it's a first derivative. Therefore, it must be a first order differential equation. The next question is it linear or nonlinear? Immediately, we see a y squared term, so already nonlinear, but even more than that now, we have sine of y and cosine of y, so it's extremely nonlinear. So right away, if it's nonlinear, it means our integrating factor method for linear ODEs is out. But we go through our list in the order that we actually want them to be solved. So first we think, okay, we want it to be linear. Nope, it's not. Okay, that's out. Next we think, okay, well, it'd be really great if this was a separable equation, because then all we need to do is get one variable to one side, like the y's on the left side, and the x's on the right side, and we just integrate. Can we do that? Unfortunately not. So it's not separable either. Okay, well, we also know about homogeneous equations. Is it homogeneous? No, unfortunately not. We see that we have trig functions here, so it's not a homogeneous equation. There's no way we could get this to be y over x everywhere instead of x's and y's by themselves. So what's the next thing we try? Well, the next thing we try is exact equations. And now we want to see if this is exact. Spoiler, it will be. So how can we check this? And what does it mean for an equation to be exact? So first, let's write this in more of a standard form for exact equations. And the way I'm going to do that is essentially I'm going to cross multiply, and then I'm going to bring everybody to one side. So what we end up finding here is that we have a sine x plus cosine y dx minus a y squared plus x sine y dy equals 0. So how do we know if this is exact? How can we check that? And the trick, which I'll explain in a little more detail why this is in a moment, but first just the how we do check it, is we have some function here multiplying dx, and some function, don't forget the minus, multiplying dy. And all you need to do is take the function multiplying dx and take the derivative with respect to y of it. So in our case, we're going to be taking the partial derivative with respect to y of sine x plus cosine y, and the partial derivative with respect to x of negative y squared plus x sine y. And in order for this to be exact, these two need to be equal. So let's check it. So this is a partial derivative, remember, so anything that is not a y is treated as a constant. The whole first term, sine x, is gone because it's treated as a constant. So we end up with 0, and then the cosine y, the derivative with respect to y, is a negative sine y. So we end up with just a negative sine y. And for the other term, we take the derivative with respect to x, so let's see. Now the y's are treated as constants, so the whole first term, which is negative y squared, is 0. And the next term has an x times a sine y, and then don't forget the minus sign. So we just end up with a minus sine y, which is that. And we see that these are equal. And that means that this is exact. And that's how you always check it. The term that has a dx, you take a derivative with respect to y, and the term that has a dy, you take the derivative with respect to x, and they have to be equal in order for it to be an exact equation. And be sure not to miss the minus signs. So now, if you want to hear me go through a little bit of the idea of what exact equations are all about, you can stay here. If not, if you want to jump to just solving this, you can look down in the description and click on the timestamp to skip over this. So if you decide to stay with me, let's take a look at this a little closer. So if we go back in our minds to something like Calc 1, and remember that if we had some function, for instance, of x and y, we could write a total differential out to be something of the form like df dx times dx plus df dy dy. Now, if we look at our equation, we see actually it's in a very similar form. And we wonder to ourselves, is there some function like f that maybe this is df dx of, and this, don't forget the minus sign, is df dy? Does this function f exist? And if so, it would essentially be our solution. And now we also see why we have this check for exactness in an equation. The mixed partial derivatives, df with dx dy and df with dy dx, must be equal for it to be exact. And we see that from this total differential here. More than that, though, we see that this is equal to 0. So if it was some total differential equal to 0, it would mean that our function f would have to be equal to a constant. And of course, you probably learned in class, this is the whole idea of exact equations. We want to find this f function for our specific case in our equation, and then set it equal to a constant, and then basically we're done. So let's see if we can do this here. So let's clean this up a little bit for everybody that didn't stay with us here. They don't have to know about this. Okay, so we're back. So here's our equation. What do we do? Well, our guess is that there's some function f that has a df dx equal to sine x plus cosine y, and it has some derivative y, partial derivatives, right? Don't forget the curly d is a partial derivative. So some df dy, don't forget the minus sign, is minus y squared plus x sine y. Now it's our choice. We can pick one of these and integrate with that particular variable to get started toward finding what f is. So you look at this and you think, okay, what's going to be easier to integrate? Personally, for me, I think this looks much easier to integrate than the bottom one. So let's use the top equation here. So we have df dx equals sine x plus cosine y. In order to get f, we have to integrate both sides with respect to x. So let's do that. Dx, and over here we have df dx equals, and again, dx, and we have sine x plus cosine y. Well, the left-hand side is just plain old f. And the right-hand side here can be broken up. Remember that integrals are linear, therefore they can be distributed. So this becomes just sine x plus integral dx of cosine y. So let's solve these. So first this is just f, right? So first with the first integral here, the integral of just sine x we know is a minus cosine x. And then plus, what is the integral of cosine y with respect to x? Well, cosine y is a constant with respect to x. Therefore, we end up just getting an x tacked onto it. That's all. But, and this is one of the parts that you always need to remember, because this was just a partial derivative with respect to x, there could have been some function h of y, it's only a function of y, that was originally there, because if I take a derivative only with respect to x here, that function h would appear as a constant and would just totally disappear. So we have to kind of cover ourselves here and say, well, there could have been a whole function that was only a function of y here. So we write it like that. And this is in place of a constant of integration. We actually get a function of integration in this case. If we had chosen this equation and we integrated with respect to y, then this h would be a function of x only. So here we are now. We're almost there. We almost have our function f. So what do? Well, we also have this we can't forget. So we take a derivative with respect to y only, a partial derivative with respect to y. And what do we get? Well, this first term, cosine x, disappears. There's no y's anywhere in sight. The next term becomes a minus x sine y. And then this function h is just h prime because it's only a function of y. So that's df dy. But then, of course, we also know that df dy is equal to this. Therefore, this must equal a minus y squared minus x sine y. So let's compare both sides. We have a minus x sine y, and we have h prime and a minus y squared. We see immediately that h prime of y must equal minus y squared. That's great. But, of course, it's h prime. It's a derivative with respect to y. So in a way, we kind of have a new differential equation here, which is that dh dy is minus y squared. But it's perfectly separable. So let's separate variables here, and we get this is just a dh over here, right? And this becomes a minus y squared dy. Integrate both sides, and we have h equals, here, remember, it's just a power law, so we add 1 to the power and then divide by that power. So we get a minus y to the 3 over 3. Now we get a real integration constant here, constant, no longer a function. And we have h, our function h. So then we remember here what f is, and we can replace our h with what we now know h is. So we have that f is minus cosine x plus x cosine y, and then it was plus h, which we now know is a minus y cubed over 3 plus a constant of integration. So we have our full function f now, whose derivative with respect to x gives us this guy, and whose derivative with respect to y gives us this guy. Then we have to remember that f has to be set equal to a constant. So let's do that here. Let's just maybe copy this to make it easy. And this has to be equal to some constant. Let's call it capital D. Now here, of course, we have two constants, but it's a first order equation. That can't be. But we also notice that if we just subtract c from both sides, over here, we end up with a d minus c. But those are both constants, therefore this itself is just a constant. Let's call that a big K. Therefore, let's rewrite this here. We have a minus cosine x plus x cosine y minus y cubed over 3 equals big K. And now we're done. We can't solve this explicitly for y, so we have to leave it implicit. And we're finished. This is our general solution for the differential equation. That was exact. But of course, we can find k if we're given a condition. Here, we're not given a condition, therefore it's even easier, and we're finished. If we were given a condition, we would plug in for x and y and solve for that k. So that's it. This was a first order, nonlinear differential equation that we found was exact, and therefore we used the methods of exact equations to solve it. So come back next time if you want to talk some more about differential equations.